Okay. Good afternoon, everybody. How are you doing? How do you accidentally drop a course?
I know, right?
That sucks. Okay, so today we're going to go through details as we left off last time. We started talking about orders of processes, and I asked you guys to come up with an example of a reaction that would fit sort of buckets of a traditional or sort of archetype second order reaction, a traditional or archetype first order, and a zero order. Any suggestions? Like, pick one of three: second, first, or zero. What do you got?
You didn't specify like what type of chemistry. So
Could be
first
anything.
order would be like nuclear decay is absolutely perfect first order.
Right, so first order would be decay, right? So that would be like a radioactive decay. When you guys have looked at things like half-lives, right? If you guys remember back, we studied those as prototypical type things. So that's like uranium-235 becomes something else. And really, again, what that is there's one molecule undergoing a rate constant. In this case, it's just the decay constant. That is a standard first order decay. Any reaction where you've got, let's say, some substrate which then turns into something else, and this could be maybe not, well, solvolysis might be. Like, so let's look at this. If I gave you, let's say, benzyl bromide, and I was going to dissolve it in methanol, and as long as the methanol was very high concentrations, the solvent, would you guys agree this looks like a first order process, right? Even though it's an SN2, right? What we're doing is oxygen is going to displace the bromine. Formally, what this is going to be, the rate of the reaction will be equal to some constant times the concentration of, we'll call this guy A, my benzyl bromide, right? Times the concentration of methanol, my nucleophile. Why is this going to be a first order process?
If it's a solvent, it's like a high enough concentration that it's pretty much constant.
Yeah, this is their pseudo first order, right? Effectively, we're saying any change in this concentration is negligible, so D-methanol dt is basically equal to zero. It doesn't do anything, so this reduces where that concentration actually becomes part of the constant. It's the constant, the K of that value multiplied by the effective concentration of the methanol would be the real K that we're measuring for that system. Okay, what about, here, let's add one more page. Add a page. Okay, that's first. Second or zero?
Zero for heterogeneous reaction.
Zero, you're going to say a heterogeneous reaction. So what do you mean? Give me an example.
Hydrogenation, palladium charcoal.
Hydrogenation on, okay.
To the surface of that material.
Okay, yeah, not bad. So what you're saying is, like, let's say I take an alkene. I'm going to react it with hydrogen, and I'm going to react it with catalytic palladium over carbon, right? And it looks zero order because it's, like as you said, it's kind of related to the number of active sites on this. So mechanistically, this should not be zero order because you're going to have, you can think of the elementary steps that are involved in this, right? There's going to be the alkene binding to the palladium is going to have to find the hydrogen. This reaction will go faster and slower as you change the partial pressure of this, but I agree with you, while it's running, it's probably going to look zero order. Observationally, you're going to see zero because it's really just related to how many active sites there. It's running at what we would call V max. Do you guys remember this from things like Michaelis-Menten? It's going as fast as it can. It doesn't matter if this thing is a Porsche, you're stuck in traffic. Like you are going as quickly as it possibly could go. Yeah, and again, but does anybody else have a zero order process? Yeah.
Like electrocyclization is like photochemical?
Photochemical is a big one. If you look at, but same thing, these are always cases, first of all, there's no such thing as an elementary process that is going to be zero order. You can't have something with a single transition state that would look zero order. It's not possible. The only way you get zero order is where you have some kind of a steady state system where the slow step is also coupled to lots of fast step that's building up that process. And the thing that's really important about it is it will be zero order for fundamentally some finite part of the reaction. When you start this reaction up, it will absolutely have order for some very small fraction of time as you're reaching steady state. But once you're at steady state, you've saturated all your catalytic sites. Now it will behave according to that. The very end of the reaction, as you start to lose the last couple of molecules of alkene, or as the catalyst starts to deactivate, now you'll see order behavior that'll come back in. So the interesting part about zero order processes, mainly for chemistry, It's a very common observation. It has to be coupled to a multi-step process, and it's usually the steady state chunk in the middle of the process, not average every day. Okay, that means who's left? What's second? Come on, this is the gimme. SN2, yeah. A standard SN2 where we had, let's say, the nucleophile. Let's say, alkyl thiol plus, we're going to do just a simple bromide. And this is being done in something like THF, right? As long as these two concentrations, X and Y, as long as the approximate concentration of X is near the concentration of Y, this will probably behave like a standard classical second order process. It's a single elementary step with one transition state, right? Yep. So in that same one, which of these corresponds to, if you had to look at them as overall processes, which is a zeroth order, which is a first order, which is a second order? E is 0. And why? What are you doing for that part? Like, how are you making that conclusion?
Well, it's just like a concentration on the y-axis and going down.
Yep, concentration time. Yep, that's exactly it. Okay, so the first order process, graphically.
It would be, oh wait,
You were going to say C, weren't you?
I was gonna say C, but it's gonna be F.
Yeah. So remember, that's the thing. So you're looking for ln on this axis, but it's ln of a starting material decreasing. That's the classical one because that's what follows in the integrated rate law, right? We're looking at the differential. It's not the rising concentration of a species. That would be a product forming one. And again, ln of product does not work in this way. Yep, absolutely. F, what's the last one? Second order is no trick. Okay, yeah. It's going to rise over time, because remember, in the first order, this here is negative k. When you do the 1 over, and if you did the integrated rate law, that is just equal to k. So it's going to be a over this one over here. And it's that 1 over starting material concentration over time. Yep. Again, this is only really useful as a general metric for the overall order or overall performance of a simple system. These are idealized too. Even a second order process like this gets a little bit weird. It really is talking about A plus A becoming product, right? It's when you have A and B as two separate species, the graphics look a little bit different just because you have the two component. All right, so last little part we're going to talk about today is the final stuff of definitions, and then we're going to start getting into kinetic modeling. So definitely for Monday, make sure you've got your laptops set up with Copasi. If you have any problems installing it, please do let me know. If you use a Mac, for a PC, at least last I checked, should be pretty simple. Download for your PC. Copasi Online is a simple download. Usually the website's supposed to scan your current version of hardware and software and recommend the version that should work with your OS and everything else. Same thing should happen for your Mac. Now, again, the main difference, there are really old Intel Macs. Most of the common sort of M1, M2 are what are called ARM Macs. That's the version you should want. The one thing that's a bit of a trick is, Apple closed ecosystem, when you try to download something that's not part of the App Store, Apple will immediately flag it and say, this is obviously malware, do not install it. You have to go and actually give it rights and permissions to do this installation because it's not part of the official sort of download. And go ahead and infect your computers, it's fine. But that's the one part that if you don't get through the gate there, but do sort of turn it out and try it. So again, for definitions, everybody should be familiar with this. A reaction mechanism is a multi-step transformation going through a sequence of elementary steps. Those language are the most important part, right? What we're going to be doing is talking about this interconnection between elementary steps, which the individual ones, really we break that down saying that is a single transition state that's involved there, versus the overall reaction has multiple different transition states. Just in general, every elementary step has its own rate law, rate constant. And then the aggregated reaction or the balanced chemical equation will look simplified. Now there's kind of two ways to look at this. A true mechanism will have a mathematical representation which is always true. So in a case like this where I have 1, 2, 3, 4 elementary steps, that means you've got 4 transition states, 4 Ks associated with each transition state, and intermediates. In this case we've got light blue, green, and yellow as your intermediates. And we can derive a rate law that talks about all of those species. If you go and run this reaction, typically we get what's called the rate determining or rate limiting step. Has everybody heard of that part before? It just means when you run this, it's not likely that the absolute Ks of each step is identical. One of these, let's say this one here, is the really slow step, which means the reaction kind of simplifies to this goes in, that barrier is the most important one, and it just, the math of the whole thing will simplify down looking at facing that particular transition state. So the problem is observationally, empirically, these rate laws have to be done by running reactions and measuring kinetics. But under the surface, rates and transformations that are too fast, where there can be buildup of these intermediates, you may not observe. So they end up simplifying down mathematically. So there's always kind of these two perspectives you're going to run into when you talk about rate laws. In the end, the overall reaction is just in and out. That's the balanced chemical equation we're usually talking about. The overall mechanism is all steps, where again, this is where if you're talking about second year OChem or something, it's every step where you draw a double-headed arrow describing bond formation. These are the ones where usually what we're doing in a proper reaction mechanism is each of these represents a single transition state. You're not trying to abridge or rush through. In other words, in second year we would say, hey, for a acetal formation or whatever, you're allowed to kind of warp speed through a bunch of proton transfers. Not allowed, right? If this is a proper reaction mechanisms, you're trying to imagine that each transformation is just a single transition state, meaning following whatever bond rearrangements that are involved there. If you're suddenly rearranging 6 or 7 bonds in a step because that's what your arrows are talking about, that's got to be a pericyclic reaction or like an extended pi system. They can happen where multiple electrons are happening, but think of it in the sense that there's only a single bond-forming breaking transition state with no intermediates on either side. And elementary steps are just that. They are only involved at a start and finish where there's a transition state connecting those pieces. Again, the difficulty with this is people will have different levels of simplification that they do implicitly. It's the same thing that happens with organic chemistry. We may not tell you what your solvent is, but we give you a common reaction. We've sort of abridged out the fact that, maybe I don't mass balance with my salts during my workup or whatever, but implicitly they're here. So what I want you to kind of think of it is, that's the highest level overall one. The individual steps themselves is we're being very rigorous about what your mass balance is, where your atoms are in your transition states. Your reaction mechanism, when we have the full one, will be those individual collection of steps. But when we start doing actual kinetics, some of these steps may disappear just because they're too fast kinetically to observe, and what you'll get is a sort of a hybrid of these two. Again, this is just simple terminology. Everybody should know this. An intermediate is something that is formed and uses up. The catalyst is something that is consumed and then coming back out. So again, very common. This is what we tell you guys in first year. If you've built anything by IKEA, you have done sort of a multi-step transformation or a reaction mechanism. So again, the analogy, that's your overall reaction, stuff you start with and stuff in the product. The mechanism is the individual breakdown steps, the sequence of steps that have to happen, where again, rate limiting step probably here is, this is the always one for me, where you're actually starting drilling screws and stuff. And then the elementary step is just focusing on one step. So DFT would look at this and say, what is my transition state for this particular transformation, right? The thing that is really difficult, and again, depending on how much you've done, you need to sort of move back and forth between the language we've applied in things like ChemDraw, where starting material becomes product. But this energetic diagram should always be sort of locked into your head. And it's something that we'll come back to a couple times, but just as a quick poll, what's your comfortability if I said the reaction is fast? Where in this diagram are you looking for that information that backs up that statement? Delta G, but where is it?
The change between reactants and transitions.
Yeah, so delta G naught, right? Or delta G double dagger, right? It's going from here to here. You're saying that is where you're looking for kinetic information to get to that barrier. That's where you're talking about Arrhenius and things like that, right? If I said that the reaction was most stable or the most stable product is happening, that's the energy difference here, right? It's here to here. So if I'm talking about examples of selectivity, if one starting material could make more than one product, you know the difference between a kinetically selected reaction, something forms fastest, versus I made the most stable intermediate that then went on to product, right? And so, and again, you probably have all have done this implicitly, but we're really going to try and dig into this. And what's really important for this next stuff we're going to work on next week, you want to sort of cultivate this philosophy of if you're drawing out multiple steps, you're kind of coming up with a mechanism, you can kind of implicitly say, I know I'm making an unstable species. So in your mind, you're saying, okay, the transition state might be small, but I'm climbing uphill to an uphill energy over here. This diagram is something you should be kind of populating as you do multiple steps. Are you guys comfortable with drawing energy level diagrams for multi-step transformations? Kind of, sketching out. You don't have to have them implicit, but this relative energy thing is something you should really get used to. One of the nice things, at least in terms of simplification, when we talk about elementary steps, we really only see things as unimolecular, bimolecular. Those are the only kind of ones that exist. We're not, almost impossible to see a termolecular event. If you have something that requires 3 pieces to come together, it's always going to involve something binding to a catalyst as a binary event, then bringing the other guy to the party, which is another binary event, and then there's a breakup or something from that part. So basically, no matter how complex any reaction is, it's either going to be one molecule falls apart by itself, or one molecule finds one partner first that then finds another partner as a series of bimolecular events. So when you're actually building out your reaction mechanisms, these are the only ones you have to really focus on. What it also means is if you're proposing a mechanism that requires 3 or more molecules to come together, you've done something where you've aggregated too many elementary steps at the same time. Break it down. And this is where order of addition of which happens first becomes the real key for looking at reactions, right? So, yeah. Remember, we've said this multiple times. You can't get a rate law from an overall reaction. Your elementary things is what happens for this, for the stoichiometry is what sort of comes into our mass balance. And going back and forth is how we're going to start building up mechanisms. So this is just that document we said before. Thermodynamics is always the energy states of stable parts of our species, where the reactant to the transition state is our speed. And remember, this goes in both directions, right? Does everybody know what we say when I say the principle of microscopic reversibility, right? Implicitly, we say that is really the same thing as that, meaning that it's going through the transition state. Really, there's no element of time here. Molecules and reactions, if you're saying a starting material can become a product and you've defined a transition state, there is not a special or different transition state to go in the other direction. They must pass forward and backwards through that same one. This is where, does anybody remember in DFT, how do you define a transition state? When you're doing like a geometry optimization, if you give it to Spartan, there's a really specific thing mathematically it's looking at that it knows it's a transition state.
The potential energy surface.
Well, that means you'd have to actually calculate every point on it. And you're right, it's a saddle point, right? You could do this where you're saying, I will draw a particular geometry in one place, and then you could plot it out that way. That's true, but there's actually a more efficient way, yeah.
When the derivative is 0?
Yeah, sorry. Actually, I'll go over here because then it's on the screen. You're getting closer. You're saying if I had...
Highest energy.
Yeah, like you're talking about like a saddle point where if I start here and I measure like the geometry, I come up to some high point and come down, there's another sort of a third dimension, difficult to draw here, it's like a well between 2 different mountains, right? That's what you're sort of describing. That's kind of what you said too. But think about it in the sense of if I am a molecule, and this is my sort of bonding axis, right? If I had sort of an A is bonded to B, where I'm actually modeling breaking that bond. So over here, let's say I have A bonded to B, and on my product, I have B negative and A plus, where I'm physically separating those two. What's the only thing that's happened going from AB to the 2 parts? One bond break. Bonds vibrate, right? If you're doing this transition state and you're moving through this energy surface, and whatever that atomic motion is on the order of a normal bond vibration, that's considered a departure, right? So if I was going to model this in terms of not an individual energy profile, but say there's taking a molecule, giving it energy and just letting it vibrate. As long as it's vibrating, I'm on this side. I'm hitting the potential well of that bond vibration stretch. It's not going any farther. If that bond vibration, or if the lifetime of this thing is on the order of a bond vibration, that's the actual bond fracture, right? If this thing up here can only last as long as a single bond might vibrate, all you're really modeling is the bond vibration, and then it just keeps going. It never comes back again. It's breached or gone past that point. So the thing I'm trying to emphasize there is when you start to mix these things, this is really just vibrational kinetics looking at an individual bond component, right? So you're really fracturing this bond by looking at that the energy where it's escaping the well that was sort of holding it hostage at that part. So in general, again, you guys should remember this part through. The delta G double dagger is the energy vibration up to our activation point, and we're going to come back to this when we start looking at how we impact the system. Remember, this is really where our K comes from, right? The K, or reaction constant, is fundamentally tied to that energy, the barrier that we're sort of, this is where transition states theory sort of grounds that potential necessary to actually break this. Versus the selectivity is between these two. That's our overall energy difference between two different molecules as you go through. But once again, speed is located here, and selectivity in terms of relative products are over there. So we start looking at multi-step reactions. All we're really doing is starting to chain these pieces together. The hard part behind it is you need to rationalize, like if you take a multi-step transformation and you say, okay, reactant goes to product, if there's an intermediate, what we're saying is it must exist on this surface in this well, meaning it has a lifetime longer than a bond vibration. Otherwise, if it's a bond vibration only, you're talking about one of the transition states in those sorts of cases. Generally, too, an intermediate, they can be more stable or less stable than our reactants. Typically, though, if you're talking about a transformation, and again, as a wider rule of thumb, most intermediates are usually higher in energy than your starting materials. Why might that be true? Give me a reason why that might be a case. It would just be there, right? Like if I had something, I was holding in a vial, and there was some simple transition state to make a much more stable species, it might just spontaneously do that. Now, it depends on what it is, right? An acid chloride. The carboxylic acid is a lot more stable than the acid chloride. So as long as I keep water away from it, I can keep it away from that well because I've prevented that whole reaction possible, right? But if you imagine that this was here, if this was my acid chloride, as long as I have water, there's potentially a carboxylic acid that's down there somewhere that it can relatively easily access, and I have to chop off that whole part of the diagram by preventing water from everywhere being near it. So generally, yeah, like there's the process, if I've got something I can hold in a vial and I'm going to do something with it, we typically are sort of climbing hills as we go that first, or we have to add something that's going to be going up in energy before we do. Or we've created this very high energy molecule and we're keeping it away from absolutely everything else first. So a very strained molecule. You've made an azide, a pyrophosphate or something, but you've done specific conditions and then isolated it from other components. What I'm getting at is when you start to chain together these steps, don't kind of check yourself that you're not violating your own rules. I am wearing blue shoes today. I hate wearing canvas shoes. Wait a minute, these are canvas shoes that are blue. What I mean is when you start to actually chain together steps, you might say, I have a reagent that is very stable. Oh, but it's forming something that is very unstable, and it's going to happen very slowly. Well, that does not match what I'm showing you here in my diagram. In this diagram here, that first step is a relatively small delta G double dagger. So the statement I made, if I'm making a mechanistic hypothesis that a starting material takes a long time to make that intermediate, that's not reflected by the energy level diagram I've had. It's something that we'll have to sort of drill down into with specific examples, but this is, I guess the difference is going through and mentally picturing these energy diagrams and then rationalizing those with what you think is physical reality about molecules. The number one thing people make mistakes in is going back and forth between these two worlds is disjointed, right? You'll make statements like, I am making, oh, my intermediate forms very quickly, but your energy diagram, it has something like that, where the second step over here is much smaller. That's not true based on what the data that you're presenting in the system is. So, a paper I want you guys to please go and find. It is definitely older than everybody else in this room, probably. This is Chem Ed, and this was a guy, a kineticist, that was basically just wanted to clarify how do you actually think about multi-step transformations? So for example, Have you guys heard of, if I looked at this diagram I'm showing you here, I'm starting at A, I'm going to B. Can everybody see that we're probably forming a more stable product, right? So in this diagram, A goes through a transition state to an intermediate. That intermediate goes through a transition state to a product. Now we haven't drawn any numbers on here, but I have a two-step transformations. Everybody can see that's what's going on here, right? Which is slower, the first step or the second step? Second step is slower than the first step. Does everybody agree with that? Anybody want to fight that? No, like why? Why do you make that conclusion?
Bigger hill to climb, so delta G double dagger is larger on the second.
Yeah, you're saying delta G double dagger 1, and this one is delta G double dagger 2, and we're pretty sure delta G double dagger 2 is greater than delta G double dagger 1. Everybody agree? What does that mean about the size of the K's? Which K is bigger? 1? Okay, good. Tiny delta G, big K. These are inversely proportional. High K values are fast reactions because remember, it's proportional to your overall rate. Your rate equals K. So yes, first step is going to have a big K, small barrier. And I agree with you. Second step should be faster than the first. Which is your rate determining step? So this is a problem known as highest peak versus biggest jump. So think about, and this is why analogies are both good and bad. Imagine this is a mountain range, right? And I'm sitting here at this start, and I have only enough oxygen or energy to get about here. I can clear this second peak here. I have enough to get over this one, but I don't have enough to get over that first one. Can I even make the ascent? Because remember, this is also energy conservation is what you're saying here. If I don't have enough energy to clear that first peak, how the heck did I get over the second one? Even though maybe I have just enough energy to clear the second one. So that's the highest peak. Even though it's the smallest one, the highest peak might be the thing that's killing me because I do not have enough energy content in the system. It's one way to think about it. You're right the other of, okay, first peak is fast, and then you get into an intermediate, and then the system will pile up at that intermediate, waiting for the second jump to happen, right? That is also true. The real answer here is, it depends. It comes down to how big those two numbers are. Usually, it's delta G between two. Like, it's a lot easier to look at it from this perspective. What if I asked this question? You are sitting right here at this intermediate. Which way are you going, left or right? So who says you go here? Okay. Who says you go here? Because that jump is smaller, right? Potentially. Like if I gave you the numbers, again, this is welcome to a scribble on a page, but if this, let's say going this way, that delta G double dagger, we'll call it delta G negative 1. If delta G negative 1 was smaller than delta G2 going that way, which one wins? So delta G minus 1 is smaller, it's faster, but delta G2 is bigger. Who still wins?
Well, it depends on how much energy you have.
It's not just how much energy you have.
Depend on the stability of the product.
That's the case, exactly. If I were to snapshot it, you're right. Basically, this is a case where this is like being young and deciding that you're going to be a movie star. I'm sitting here. This might be an easier barrier, but I just climbed up to a higher energy state. And as long as that transition state is accessible, this is going to be where your population is. That equilibrium might set up. You're going to have both of those species very quickly, but over time, you will find your way to a nice house in the suburbs, and you will settle down, and you will be a broker or something, right? So that's where there's a kinetic element, where some of who's winning might be a time frame. Early in the reaction, yeah, A wins, but over time, it sort of reformats over to B. This is where looking at these diagrams, the other way to do this, if I was to look at it differently, I'm showing you this where I've got this left and right. You've probably seen the same diagram where I have I here, and I've got this versus, let's say, bigger barrier, but that, right? That's your classic diagram for a kinetically trapped reaction versus a thermodynamically trapped reaction. So if you've ever seen single material and then two pathways moving forward, it's really the same thing as folding it open like this, right? There's nothing different between those two representations. But point is, that's why grab this article, go look at it, right? He discusses some of these points, and what it comes down to is he talks a little bit about in the original sort of definitions of kinetics, they kind of thought of things moving from bucket to bucket, what they called flow. So this is where the analogy was, if I'm in a river, or if I'm in a bucket, excuse me, and I poke a hole in the bottom of the bucket, dripping out of that one, I move to the next bucket. That's kind of energetically what I'm trying to describe here is I start in a certain state, and if I have a small hole in the bucket, I have a small drop, right? So that means the first bucket will basically be driving the bus because small drops into the second bucket with a big hole in the second bucket means it rips through there. Second step I don't even see because I really see the first bucket and then the last bucket. That's it. That flow analogy works for that kind of step where that first step is your rate determining step. If you do the same thing here, the math that you would actually predict watching that flow analogy breaks down because you have a fast reversible step, which literally the gravity analogy of water flowing downhill doesn't exist here, right? You cannot take a bucket and hole analogy that predicts this because that first step is rapid equilibrium. You know, if I were to look at this step back and forth quickly like this, means that this is still my slow step, but I don't have the same, there's not a ton of this material. It never really builds up, right? It's just there transiently. That's an SN1 reaction, most common, right? Where you have to climb uphill from a rapid carbocation formation and then elimination. So the examples he gives you is, carbocation formation for like an acetate elimination. He gives examples of like oxalate redox type chemistry. So these are like pinacol kind of reactions. You guys probably remember these ones, right? These are sort of protonations or like aromatic substitution reactions of benzene where it's acting like the nucleophile. All of these are examples where you have to have a very rapid equilibrium to a high energy intermediate that never really builds up. And that's where it violates the flow analogy. So the thing he kind of discusses through here is there's not one case. So if this is your energy surface, highest height and biggest jump starts to get really convoluted, right? Because you can't be as general in saying, well, where's your rate determining step? This one will depend on both the concentration and the absolute K of each of these steps. You'll probably have a population. It gets very difficult to call one guy the rate determining step because it'll depend. And that's where the modeling step really comes in. As you start to get to these multi-step transformations, it is no longer as easy to just point to the thing and say, well, there's your rate determining step. No, it's complex, right? It'll break down. We will take on the two easy ones. This is what we probably learn in first and second year. First step is fast, and second step is fast, right? These are ones where the math is actually quite simple and helps you to sort of frame your concepts. Okay, first step is slow. Second step is fast. This would be something where you have that kind of bucket analogy, right? A turns into an intermediate. That's a slow step. Intermediate goes on to product. And like what we discussed, because if I was starting over here and I get over this barrier, once I'm here, it's unlikely I'm going backwards. The barrier's too high. This is pretty quick. I go on to product. So the concentration at this point, at any point in time, is going to be vanishingly small. It goes through there, but I probably can't see it. It doesn't stick around for a long time. Its lifetime will still be longer than the vibration of a bond, right? It's still on the low energy surface, but its population will be very, very low. So if I did a Gaussian transform, like a DFT calculation, it'll exist. Like I could technically isolate it. It's just that on this energy surface, it's much more likely to just go onto your product instead of stick around. But again, the only difference between that compound and the transition state is if you were to go and look at it, whatever axis you're looking at the bond stretching or breaking, however it formed, it could vibrate along that axis for a couple times before it fractured and went on to product. The kinetics of this are pretty easy, right? If your first step is slow, the K of that step is kind of driving the whole bus, so the rate is just equal to whatever you start off with, your gas, your A material, and really that first K1. After that, it's all downhill, and I'm good enough. I can calculate everything from here. So the rate determining step is the first step, and it's just rate is equal to K. This is how we get what looks like to be maybe a second order process, looks like a first order process. Now again, this is not an SN1 reaction. SN1 follows that first jump is slow, first jump is fast, second jump is slow. So these are easy, math is easy, this one should be very common. Sorry, that should be very familiar. It's simple. A lot more reactions we end up dealing with in OChem look like this, right? You take a molecule, you heat the crap out of it, you start to populate a high energy intermediate that then goes on to product. This is an SN1 chemistry, where that intermediate is actually forming quickly but unstable. So there's a very rapid equilibrium set up with whatever that high energy intermediate is. This is harder mathematically because what we get here is if I've got the same point, that is my rate determining step. If I'm going to draw the rate equation for that, the way you do this is you separate that second step, that's kind of the one that's driving the bus, and the rate of that second step is just based on what you see on this specific elementary step. It's your starting materials, your intermediate, multiplied by the rate constant for that. So the rate of formation of my product is really just going to be K2 times intermediate. And just like the first example, if this is my RDS, the rate is basically controlled only by the RDS. The problem we have here from studying the reaction point of view, it requires me to know the concentration of this intermediate. And that may not be possible. If this was a carbocation generation, I'd have to measure that carbocation. It's not directly proportional to my intermediate concentration. So now we have to apply simplification some way. This is where we could say that if I believe this is a fast enough equilibrium, this intermediate concentration is basically equal to A. If it's fast enough, we can kind of scrub it away and say it's only equal to the second step. Or what we have to start doing is actually come up with a generalized rule to do this. We have to actually go and mathematically come up with an expression that talks about this intermediate concentration. This is where we need to know how high an energy it is, or if it's connected to a multi-step catalytic cascade. This is steady state approximation. This is what we usually have to do in this case, right? Does everybody remember, at least conversationally? Okay, so I'm going to skip over the fast equilibrium approximation. This is one way to deal with it. Much more common is steady state. The reason why is steady state approximation is the most complete general description mathematically of catalytic reactions, and we're going to focus primarily on these multi-step catalytic reactions. This is a lot more useful to you guys. So when we say steady state, we're saying, okay, A is in equilibrium with an intermediate. That intermediate goes on to product. Steady state just means the intermediate shows up and roughly, for the course of the reaction, it's level. The relative change in concentration of the intermediate is equal to 0. Not the concentration of intermediate is 0. It shows up. We have a concentration of intermediate. It's just that steady state means it's not changing. We set up an equilibrium and we hold it. Now what you'll start to see, especially as you start to play with kinetic modeling, the number of systems where steady state isn't actually held is shocking. This is math. Math makes it simple. We do use steady state approximation a lot. It's important to look at the steady state approximation as a way of sort of taking apart reactions. The thing I'm going to put an asterisk on is most practical reactions, steady state, this whole concentration of intermediate is constant with time, is usually only held for a fractional part of a reaction that we start. If you take a proline catalyzed reaction and run it, you'll see steady state sets up. It runs for maybe 10-15% of the reaction, and then you start deviating from that. So this is useful in sort of a conceptual way, but that's where, again, applications of this for actually solving true rate equations and why they deviate from ideality is way more common than you think. That's why we need something like Kopassi. So the math. Has everybody done derivations of rate equations this way using the steady state approximation? Okay, so tell me how you do it. Again, I'm only going to touch on it. I want you guys to practice it. Your first assignment, again, the way I want to work on assignments in the class, I will give you guys problems to work on. I am not going to grade them. We will discuss them in class. These are not part of your final marks. You better do them because they will be important things that I'm expecting you've gone through the math and you understand. So please do that. But again, I'm treating you guys are adults. I told you to please wear clean underwear, show up on time, whatever. You're doing your homework on it, right? But this is not like, I'm not grading it so you don't have to do it. No, that's a bad choice. I want you to work through this and actually do this longhand so you guys can practice this. If you take any system that has 2 steps, for example, the simple one, A is an equilibrium with an intermediate. That intermediate goes on to product. I am talking about how many elementary steps as it's drawn out here. 2. There are 3 individual steps. Mad points. What I mean, again, this is an equilibrium, but remember, an equilibrium is just one elementary step one way and an elementary step in reverse. They're related to each other, but break them down as 3 individual components. So you're looking at that reaction, and that reaction. Straight out. And again, that's just basically count the K's. That's how many elementary steps you have. Okay, so you write out the rate law of the final step. When you're doing a steady state approximation, we don't care which one is fast or slow. We say, I have a mechanism, and I'm going to start working backwards like a chain rule. The rate of formation of any product must be equal to the step just before that product times its K, right? So if I have a multi-step transformation, product formation, rate of product formation is just going to be K2 times intermediate. That's just, it was formed from that intermediate. I don't care if it's slow or fast, I write out that expression first. Then I find any intermediate in the system and I find an equation that describes how does that intermediate form or is broken down. And that's why there are 1, 2, 3 terms, because there are 1, 2, 3 ways that you will impact the intermediate. And we say that the rate of all of those is equal to 0. That is the steady state approximation. That's step 2. Now you algebraically solve for it. Get intermediate on its own, which just means move stuff where you have to move them so that you actually have a term that expresses this. This is the most heavy math lifting you're going to do. It's just move things around and don't jump steps so that you don't create variables, right? But it's just isolate intermediate, solve for x. Once you've got that term, you go back to your rate equation, your first step. You now have a term for intermediate, and you sub all of this into that term. Then you get an expanded term. And then finally, it's simplify. So here, all I'm doing is this term here, intermediate, is actually all of that. That's what this is. And I've got K2 outside, so I just multiply K2 in. If you've done enough of these, this is a pattern that will always repeat itself. This is what we call the 1+ form. A multi-step transformation like this, if you notice, it is always going to have on the numerator reaction constants that talk about moving forward in the reaction. There's anything where you move forward in your reaction sequence, so you should have K1, K2 up there. You're going to have the stuff that makes the reaction go. Starting materials will always show up in the numerator. In the denominator is stuff that uses up or potentially impacts the intermediate primarily. This is like things that break down, reverse reactions, or in this case, the intermediate consumption over here. But you'll notice this is kind of broken up into a kinetics term. It's some fraction of all the K's kind of glommed together with whatever power law that's necessary, and then some what we call driving force, the reactants or reagents that actually make the reaction happen, concentrations associated with materials. It doesn't matter how complex it is, it'll always have this kind of synergy that you'll be able to see. So what I'm really talking about in that case, when we start to go to catalysis now, is effectively we create these intermediates. We can use the same chain rule. The one thing that gets more difficult is catalysis means we're making an intermediate and then we're regenerating a catalyst. So there's a new term that has to be part. It's no different than that last example. But now what we have is enzyme coming into the system, enzyme going out of the system, so it ends up being a little bit more mathematically complicated. If we do the steady state approximation, we can do the same thing. This step here, last step, so rate of product formation is just ES, this intermediate, times K cat, right? It's the same thing we did before where we said that concentration times that constant must equal the rate of product formation. Okay, so now we have to come up with D intermediate dt. It's going to be formed, broken down, and formed. That gives us 1, 2, 3 terms. just like we said before, and we set that equal to 0. Same thing. The only difference before is, remember, we had ES here. That was the unknown that we were solving for before. What's that? This value here. Concentration of catalyst. Really?
It's concentration of catalyst minus the concentration of ES?
That's the problem. When you say concentration of catalyst, everybody goes, oh, that's the amount of proline I scooped into the reaction. No, that's how the ES I scooped into the reaction, concentration of catalyst, that is in the absence of substrate or product or anything else. That's the true, I picked up palladium and I threw it in the reaction, that's how much I added. But once the reaction sets up, some of this concentration of catalyst is going to be distributed between two different species. Once you're at steady state, some of that palladium is bound palladium. So the E value you have here is concentration of free catalyst. So there's one more term we need. You're going to need this, which is your mass balance equation for the catalyst in the system. The total catalyst is what you weighed out, and that's going to be equal to sum of all of the things that touch catalyst in that chain. So really what we're saying is in this last equation, back here, this equation has 1, 2 unknowns. So we can't solve it on its own. We can't just simply go and solve this part of it. We need to go through and solve for both. So that's why I need this second equation, which relates ES to E, those two unknowns. Y is now equivalent to X, and now I can go solve it because that's a known value. So you go two things. I use my mass balance equation to solve for my ES, or my, previous equation to solve for ES gives me this. E total now is being expressed in terms of this species. So when you're done, d product dt, kcat ES is going to look a little more complicated than you did before. If you looked at the sequence we had, there's still concentrations that make the reaction work, but down here on the bottom, you notice you have this K1 substrate. The substrate shows up in the denominator now because of how we have this recycling part that's built into it, right? So anybody who did biochem, everybody had to do biochem. Michaelis-Menten equation, this is the Michaelis-Menten equation. This is just the steady state, or sort of the normal kinetic version of it that chemists usually look at it as, where you've got the full sum of K1, K-1, K, and Kcat. When we talk about enzyme kinetics, we start to bin pieces together. What we call Km, the Michaelis-Menten constant, is just defined as a bunch of other terms squished together. All they did was they took the individual rate constants and reactant constants, expressed it as a different fraction just to simplify the math. The Michaelis-Menten equation really existed because they wanted to get to a linearization, something they could easily do with graph without having to do complex math or complex integrals. So all they're really doing is taking that equation and simplifying it, defining this as your Km, your Kcat, which would be like your full velocity of the reaction usually is what's associated with that. You keep it up in your numerator. So usually your normal Michaelis-Menten equation is just a rearrangement of those constants, nothing more. That's where we call Vmax, which is associated with your Kcat, where you're just taking those two values, your enzyme total and your Kcat, defining how fast the reaction can go based on a certain amount of catalyst in the system. They're normalizing some overall speed of a reaction by how much catalyst you add. Because what they were doing at that time is they were trying to say, if I had to compare two different enzymes from each other, I want to make sure that the concentration of those two enzymes is somehow compensated for. If I'm going to run a reaction, I'm trying to say that this lipase and this lipase, who's winning, I want to make sure that I'm normalizing based on how much of that lipase is present, so I've got a real value that says that lipase is faster. That's why you're defining your Vmax is a combination of your enzyme total and your Kcat value of the two, right? So you're aggregating those parts. But this is where, again, you probably have seen Michaelis-Menten curves, right? If you're actually plotting Vmax, or the velocity of the reaction versus how much substrate you have, the curve, looks like that, right? If you were to increase the amount of substrate and measure how fast the reaction goes, there's going to be a part of time in these systems where a little bit of substrate, it's fast. More substrate goes faster. More substrate goes faster. And that keeps on happening until you end up with this part of the curve. What's happening over here is You've added so much substrate, the enzyme is doing the best it possibly can. It cannot go any faster. You can't feed it any more gas. The enzyme's turning over as quick as it can. And we need to know that because it's a fundamental value for certain reactions that tells us about different catalysts and their performance. Remember, this is not looking at concentration on time. This is rate against how much substrate you're looking at. So really, when we look at this, we're looking at a part of the catalyst which looks like it's first order. It is responding to the concentration of substrate, versus over here, I'm adding substrate and it is zero order. So this is the really big problem with talking about mechanisms in terms of order. As soon as you go over to catalytic systems, order starts becoming arbitrary based on this ratio of catalyst and substrate. It's no longer just a zero order process. There's going to be parts of the system that will behave first order because of the relative ratio of how much starting material and catalyst you have. And there's going to be parts of the reaction that obey zero order kinetics because the catalyst is doing its best and there's just a ton of substrate. Relative orders are what's going to have to happen here. So that's the part we're going to kick off on Monday. The thing I want you to focus on, though, is the simplification. So have you guys seen, if I look at this equation, for this, because this substrate here is in the denominator, what we're really saying is, depending how big that substrate value is, and how big the Km value is, one of those two denominators is going to rule. And you guys remember this from Henderson-Hasselbalch equations. You've done this part before where you have any mathematical expression where the denominator is made up of two different terms. I can have a situation where if this value, S, is very, very, very large, Km doesn't matter. This whole thing simplifies simply to V max. I'm saying that if this is the big value, that's insignificant. This whole thing is just V max. However, if S is really, really small, that's insignificant. You're actually in this regime here. What you're looking at those two is on the right, that is a first order in substrate system. On the left, that is a zero order system. Both are true. It depends on the relative value of the two. And we're going to go through the math and values. In my slides, I want you guys to review these ones, or this one particular. This is the Python that is necessary so that you never have to do algebra ever again. So part of the assignment I'm going to post up for you guys to work through this next week is I want you to do the longhand derivation of the Michaelis-Menten equation. Basically, you should be able to write it in steady state. You should be able to do the algebra, and you should be able to get the same equations I gave you here, right? You should be able to derive that equation, right, from just those parts. If you can do that, I can give you a more complicated cycle, and you follow the same algebra. You're going to end up with the same sort of point. You have to be able to sort of have the productive value from that. What this is, if you understand this, and we'll review through this, you never have to do the longhand algebra. You can punch this into a Python window. It will do all the algebra for you, but you need to be able to set up and run this point. So we'll go through and view this on Monday in addition to introducing you guys to Copasi. All right, have a good weekend.